Hi, my name is Carsten Benthin, and today I'm going to talk about BLOC++, our new version of the parallel locally ordered clustering approach for constructing bounding volume hierarchies. This is joint work with Radoslaw, Drabinski, Lorenzo, Tessari, and Addis, Dittebrandt. Okay, so it's pretty obvious that ray tracing has become mainstream in the interactive/real-time domain over the last couple of years, and that the bounding volume hierarchy has established itself as the dominant underlying acceleration structure. Now, in the context of supporting fully dynamic content, the issue is that due to BVH quality reasons, one cannot always just update/refit the BVH, but instead needs to rely on a full BVH rebuild. That means the BVH construction method needs to be as fast as possible without sacrificing too much BVH quality, which together is a challenging problem. Okay, so over the last decade, many different BVH construction methods have been proposed, be it top-down, bottom-up, insertion-based, for binary or wide BVHs, focusing on CPUs, GPUs, or even custom hardware. It's not possible to cover everything here, so I highly recommend to have a look at the latest survey on bounding volume hierarchies for ray tracing by Daniel Meister and Shinji Ogaki. However, I would like to point out the previous work that our approach is based on, and that's the excellent parallel locally ordered clustering, or short PLOC approach by Daniel Meister and Jiri Bittner, published a couple of years ago. It's a pure GPU-focused approach, which is conceptually quite simple and elegant, and not too difficult to implement. It's also an iterative approach, which means a bunch of kernels per iteration are launched, which build parts of a binary BVH in a bottom-up fashion. So this iterative process is continued until the whole BVH is built. The original implementation already demonstrated quite decent BVH build performance, but in this talk, we're going to show how to make it really fast. So here's a quick outline of my talk. First, I'll do a quick recap on the original BLOC algorithm. Next, I'll introduce our new BLOC++ version, followed by a simple extension. Then I'll compare the original BLOC against BLOC++ and an optimized LBVH builder in terms of BVH build performance and quality. And finally, I'll conclude and present some interesting ideas for future work. Okay, let's have a look at the original BLOC algorithm first. It starts with a so-called pre-build phase. This phase gets a list of primitives, for example, triangles, as input. For each primitive, a so-called cluster representative, or short cluster rep, is constructed, which essentially is an Excel-aligned bounding box with a bit of extra data. Then for each cluster rep, a Morton code is computed, and the list of cluster reps is sorted based on their Morton codes. The final output of this is basically a spatially sorted list of cluster reps. With the sorted list of cluster reps as input, the iterative build phase begins. This phase essentially is divided into three parts. The first part performs an approximate nearest neighbor search for each cluster rep using a predefined search radius R. It does that by scanning R elements to the left and right of a given position in the sorted list, and evaluates for each pair a distance function, which is simply the area of the pair's merged bounding boxes. In our example here, we evaluate the distance function at position C for the pairs AC, BC, DC, and EC. The nearest neighbor is the element for which the distance function is the smallest. In our example, let's assume for now the nearest neighbor for cluster rep C is A, and for D it's E. In the second part of the iterative build phase, which is called locally ordered clustering, or short LOC, we try to merge cluster reps with their respective nearest neighbor. However, only two cluster reps will be merged if they mutually agree on being the nearest neighbors. In other words, the nearest neighbor of my nearest neighbor needs to be myself. This merging creates a new cluster rep, which corresponds to creating an inner node in the inner binary BVH tree. So for our example on the right here, we create the new inner nodes A plus C and D plus E. So after creating the new cluster reps, the data of the two merged elements pair cluster rep in the sorted list is updated. In particular, the element with the smaller index is overwritten with the newly created cluster rep, while the element with the larger index is invalidated. In our example, A is overwritten with A plus C and C is invalidated. D is overwritten with D plus E and E is invalidated. In this third and final part of the iterative build process, a simple compaction step is executed, which removes invalid entries from the sorted list, thereby reducing its length. This iterative process with its 3 steps is continued until only a single cluster rep remains, which means a full binary BVH has been built. Okay, now how's this algorithm mapped to the GPU? In the original implementation, each iteration requires 5 kernel launches. 1 for the approximate nearest neighbor search, which is by far the most expensive kernel. 1 for the locally ordered clustering phase, which is the second most expensive kernel. And finally, 3 kernel launches for the compaction, which relies on a prefix sum. Besides that, auxiliary arrays for storing nearest neighbor indices, valid flags, and for the prefix sum are required. It's important to note that the typical number of iterations required per scene ranges between 50 and 150, which together with the 5 kernel launches per iteration required causes quite some overhead and reduces overall BVH build efficiency. So now with our new PLOC++ approach, we are addressing exactly these bottlenecks of the original approach. In particular, we merge phases into a single kernel launch to reduce the number of kernel launches per iteration. We get rid of all the auxiliary data buffers, which saves memory and bandwidth. In particular, we reduce significantly the cost of the nearest neighbor search. And finally, we handle the case of operating on a small number of cluster reps way more efficiently. Okay, so let's go over these changes step by step. The first question is, how can we merge the nearest neighbor search in the locally ordered clustering phase? The simple idea is to operate on independent chunks of cluster reps. So let's assume for now the list of cluster reps is divided into equally sized chunks of about 1,000 elements each. In order to perform the locally ordered clustering step directly after the nearest neighbor search for a chunk I, we need to include additional elements to the left and right of this chunk. How much depends on the actual search radius, which in this example on the slide is set to 2. The additional elements are highlighted as orange in the yellow boxes to the left and to the right of this chunk. Now let's assume E would be the nearest neighbor of D. In order to ensure that D is also the nearest neighbor of E, we need to scan R elements to the left and right of E. So this means in total we need to scan 4 times R additional elements in addition to the cluster reps in chunk I. To ensure merging consistency when processing the chunks fully in parallel, we extend the previous merging criteria to only merge 2 elements if the smaller index is included in the current chunk. So for our example, the pair, this condition holds for the pair DE, but not for the pair AB, because the smaller index B is outside the chunk I. Okay, so the processing of independent chunks in combination with the merging of the nearest neighbor search and the locally ordered clustering phase has more advantages. What we can do is we can do parts of the compaction phase in this merged phase as well, which reduces the actual compaction phase to just a lightweight version. Also, we don't need the auxiliary arrays anymore, right? For example, storing the nearest neighbor indices or the valid flags. So this saves bandwidth and instructions. We can also assign a GPU workgroup, or in CUDA terms, a CUDA block, to process a single chunk and keep all required data in shared local memory. With all that, the number of required kernel launches is reduced from 5 to just 2 per iteration. So in the next step, our task is to reduce the cost of the nearest neighbor search. Obviously, if you have n elements, the cost of this phase is n times 2 times r. Again, we operate on a single chunk of cluster reps at a time, and in order to reduce the cost, we exploit the symmetry of the distance function, which again is the area of the merge bounding boxes. In particular, we try to avoid redundant operations. To illustrate these redundant operations, just look at this example. When we start at position A and scan to the right, we compute distance A and C, but we are doing exactly the same when we start at C and scan to the left to compute distance C and A. To avoid redundancy, we store the smallest distance and the nearest neighbor index in shared local memory and scan only to the right of each element. So now when computing, for example, distance A and C, we update the distance and nearest neighbor index for both positions A and C. And we have to do this atomically, as neighboring work items / CUDA threads could access the same data. In the end, this avoids all redundant computations and essentially halves the complexity of the nearest neighbor search. Okay, in the next step, as the list of cluster reps shrinks per iteration, we will come to the point when only a small number of cluster reps remains, which basically corresponds to building the top of the binary BVH tree. At this point, launching a kernel just to process a few hundred elements is pretty much overkill, as the cost of launching a kernel is bigger than the cost of performing the actual work. The very simple solution to this problem is to first test whether the number of cluster reps is below a certain threshold, for example, a couple of thousand elements. Then launch a kernel with a single workgroup. The single workgroup performs all phases of the iteration using fast barriers for synchronization. So this ensures that the number of iterations where we need full kernel launches typically stays under 50 for most scenes. So with that, we have covered all contributions of PLOC++, so I would like to present a simple extension to make it even faster. The extension focuses on reducing the kernel launch overhead even further and relies on the previous idea of using workgroups and barriers for doing the entire iterative process per workgroup within a single kernel launch. So what we simply do is to use the already existing Morton codes to extract M somewhat spatially independent partitions. What we do is we traverse the Morton codes top down in a breadth-first manner to extract these partitions. So in the next step, we launch a single kernel and process all of these partitions independently by assigning a single workgroup per partition, as shown here in this example. Each workgroup performs all required iterations and stops if the number of cluster reps per partition is smaller than a predefined threshold. As a final step, we launch a single workgroup kernel which fetches the remaining cluster reps per partition and compacts them to a sequential list again. At this point, the build process simply continues in the usual way with the compacted list. The advantage is that with this extension, the number of kernel launches is actually independent of the number of iterations required. However, there's a catch. The resulting BVH tree will differ from the one constructed by standard PLOC/PLOC++, as the nearest neighbor search is restricted to the elements in the partition. We call this entire approach PLOC++ 2-level, as it uses a kind of an implicit 2-level hierarchy. Okay, it's time for some results. So we coded everything with the data parallel C++ compiler that Intel provides with the OneAPI toolkit and run everything on Ubuntu 2004 Linux. In terms of hardware, we used the pre-production Intel Alchemist G10 GPU, which is a kind of a big one, right, with 32 XE cores, 16 GB of DDR6 and full ray tracing hardware support. In terms of workgroup size, we use the maximum, which is 1024. And with respect to Morton codes, we used really big ones, right, with a 64-bit key and 32-bit index because of quality reasons. For sorting, we used an optimized LSB radix sort implementation. And as the default setting is to use the search radius of 16. Okay, so first let's have a look at the relative kernel runtimes using device timings. excuse me. Device timings mean we only measure the time per kernel on the device, excluding any kernel launch overhead. I would like to point out the orange and red bar of the original PLOC approach, which correspond to the nearest neighbor search and the locally ordered clustering phase. If we compare this to the corresponding merged phase of PLOC++, which is the yellow bar, we see that the merged phase with the faster nearest neighbor search basically cuts the cost in half. Also, PLOC++ gets rid of the entire prefix sum part and uses only a lightweight compaction phase. What's interesting is that for PLOC++, the pre-build phase, which means Morton code generation, sorting, etc., has already larger cost than the actual iterative BVH build phases. So in this comparison, we show relative BVH build performance speed up of PLOC++ and its two-level extension versus the original PLOC implementation using host timings. Host timings include any visible kernel launch overhead. As speed of light reference, we also include numbers of an optimized 4D 64-bit Morton code LBVH builder, which can kind of be considered to be one of the fastest from scratch BVH build approaches available. So now the graph shows that PLOC++ provides roughly a speed of 1.9 to 2.3x compared to the original implementation, while the two-level extension with its minimal kernel launch overhead increases the speed up even to 3x for some scenes. Okay, BVH build speedup is one thing, but the quality of the final BVH needs to be good enough to ensure high tracing performance. In order to test the real-world impact of BVH quality, we used the simplified diffuse path tracer as a benchmarking tool and compared the actual ray tracing performance of PLOC++ against our highest quality BVH builder reference, which is an offline CPU-based Bint-SIH builder. Here, the graph shows that both PLOC++ and its two-level extension achieve 90%, roughly 90% or more of the ray tracing performance when we would use a Bint-SIH builder, which is actually pretty good. On the other hand, the LBVH builder provides visible lower BVH quality and therefore lower ray tracing performance. In conclusion, PLOC++ and its two-level extension provide a significant speed up in terms of BVH build performance compared to the original approach, while retaining high BVH quality and ray tracing performance. But in my opinion, the biggest advantage of PLOC++ is its simple implementation. Nevertheless, we will provide the full source code of our implementation in an experimental branch of the upcoming MP4 release. In terms of future ideas, I mean, there are many ways to optimize the current approach, right? We could apply even faster nearest neighbor search. We could compress the cluster reps to save bandwidth and memory footprint. We could apply rebraiding techniques to the two-level approach to gain further quality, etc. There are many optimizations possible. Okay, that's it. Thanks a lot for listening, and I now take your questions.
Okay. Thanks very much, Carsten. Okay,
Hi.
and we have Carsten here live, and he appears to be wearing the same T-shirt, so we have continuity. Let's see. Thanks, Carsten. I'm glad you could make it in person.
Sure.
Just one quick clarifying question while other people are formulating their questions. What is the fourth dimension in the LBVH that you compared to in the results?
It's the size of the triangle.
Okay.
So you have the position, and the fourth component is the size. So you get, for most of the scenes, you get better quality with that.
Cool. Thank you. All right. Other questions? Okay. Here's one in the chat. Have you compared the relative speed up on other GPUs? Note, I'm not asking Alchemist versus others comparison, but PLOC++ versus other builders on other GPUs.
Let's put it that way. We plan to do so, but we haven't gotten around to do it. But it should be really straightforward. I mean, the implementation is really simple. So a port shouldn't take too long. That's for sure. But we tested other algorithms also on Alchemist, right? Be it ATR, BBH, and other variants.
Okay, cool. Next question also in the chat. Maybe I missed it in the talk, but did you consider leaf geometry other than triangles?
No, but the entire build process is kind of independent of the triangles, right? It just takes a bunch of bounding boxes as input, right? And you can generate these bounding boxes from any kind of geometry data, right? So the triangles is just the typical, let's say, set of models that we use, right? But it's completely independent of actually being triangles.
Okay, next question. What proportion of gains do you attribute to the reduced kernel launch overhead versus other algorithmic optimizations?
Could you repeat the question? I missed it at the beginning.
Okay, what proportion of the gains do you attribute to the reduced kernel launch overhead versus other changes?
So I think the question goes whether games are really affected by the kernel launch overhead. I'm not an expert in games, so I'm not sure how much, let's say, pipelining is done to kind of hide this kernel launch overhead there.
So gains, as in how much of the speed up is from reducing the kernel launch overhead
okay.
versus other things.
So usually it's depends on the model, but it's 1.3 to 1.4x what you save, if this makes sense.
Okay, yep.
It depends on the number of iterations, right? The more iterations you need, the more kernel launches you have, right? And the more you will save from reducing, let's say, using the two-level extension. And for example, in the paper, we used the Rangholt scene, which has the lowest number of iterations. So the kernel launch overhead is also the lowest, while I think the Bistro scene requires the most iterations and therefore sees the biggest gains with the reduced overhead.
Okay, so the number of kernel launches due to iterations is a big part of what you're solving here.
Exactly. So we reduce the number of kernel launches per iteration in the standard BLOC++ approach, and we reduce we get to almost 2 or 3 kernel launches only with the extension. So this is independent of the number of iterations.
Okay. Next question. Why does the 2-level version sometimes give better performance than the 1-level version?
This is a very good question.
And I assume that means ray tracing performance, not build speed.
Yes. So the 2-level approach relies on the Morton partitionings. And depending how the Morton partitionings are, you get, let's say, a different top of the tree, right? And there, sometimes it seems the Morton partitions do well, and sometimes they don't, right? It's really hard to say what exactly is the reason, but I think the main point is that we don't lose much quality with the 2-level approach. If it's even better for some scenes, that's great. But I cannot really pinpoint you to one exact reason. It really depends how the partitions are kind of dividing the model. And the problem with the Morton's code, they only look at the centroids, right? They don't take into account the spatial extents of the bounds.
And also, any time you map 3 dimensions onto 1 dimension, you're going to have discontinuities, right?
Yes.
And it's just kind of luck where those discontinuities fit you.
Absolutely.
Yeah. Which just an aside, this makes me think maybe the world, somebody ought to try other space filling curves because they have different properties, right? They have the discontinuities in different places and different magnitudes of discontinuities.
Absolutely. We actually tried Hilbert curve, but it didn't make much of a difference. I mean, Hilbert avoids these kind of Z structures of the Morton code. But for BLOC++ or BLOC in general, it didn't make any difference. Most likely because the search window is so big that you kind of cover these set steps.
Thank you. That's good to know. Okay, let's thank our speaker one more time. Thanks, Carsten.
Thank you.